Okay, so we're going to continue with this related rates, but all the problems we're doing today have something in common. They involve similar triangles. Now, let's just look at example 1. An inverted cone is leaking water at a rate. So for example, let's say we have a cone that's upside down and it's leaking water at a rate of 1 centimeters cubed per minute. So I know my dV dt here, right? I'm decreasing by 1 centimeters cubed per minute. The cone has a height of 9 centimeters and a diameter of 6 centimeters. Find the rate at which the water level is dropping when h equals 3 centimeters. Now, yes. Okay, so before we even start, just by going yesterday, what you would probably think we would do here is just do a product rule here, right? dV dt, there's nothing constant, nothing staying constant here. Does everyone make sense why this is not constant? Even though this is water flowing, does everyone understand that when the water flows in a cone, radius and height are both changing, right? In a cylinder, the radius doesn't change because it's stuck, right? And with the cone, the radius and the height are always going to be changing, right? So even if I do a product rule here and I get, so just let's not even bother with what the product rule is. I know that when you do the product rule, the first function has an r and then it's going to have a dh dt, right? And then I'm going to have a plus h and then a dr dt. And there's a problem here because they give us h is 3 centimeters at the end, but they don't give us the r, right, when the height is 3. However, so first let's go ahead, let's list all the information we know. We know this formula, 1/3 pi r squared h. We also know dV dt. It's leaking water, so this is just -1 centimeters cubed per minute. And we are looking for it says find the rate at which the water level is dropping. That's just another word for height. So our dH dt is our question mark. And they want to know the rate at which the water level is dropping when h is 3. So even if I did a product rule, I'll have an r, which I don't have here, right? And so even if you start with doing that, you'll get stuck because you'll have two variables. You'll have a dH dt, which you're looking for. And yeah, and also you'll have a dr dt, which you don't know. There'll be a lot of unknowns. You don't know your r, you don't know your dr dt, and you don't know your dH dt. So, yeah, I know, I remember that too. However, cones have a special property. So here's your cone. Right? No. So we have a cone and it's leaking water down here. So it's an inverted cone, right? So when you talk about a cone, they put the circle on the bottom. An inverted cone means you put the tip at the bottom. No, I don't know. No, you could get something where like, you hold something in place like this and it keeps it in place, right? Like on the side. Okay, just go with it. Okay, now my diameter is 6, so the radius is going to be half of that, right? So this is 3, and the height of the cone is 9. But doesn't it end at the bottom? What? Okay, so now, however, as we keep going down the cone, what happens is, like, let's say I make a triangle here. The triangle is a similar triangle because it has the same angle here, and it has the same angle here. And if you remember from geometry, you could prove angles are similar with an angle-angle postulate. Now let's, okay, I know a lot of you probably don't remember that. But angle-angle is one of the postulates for similarity. And since the angles are going to be the same as the height decreases, we could make similar triangles. And so basically any triangle in this thing, so for example, if I make a triangle here, I make a triangle here, the ratio of the radius to the height is always going to be 3/9. It's always going to have a ratio of 1/3. This length of the triangle versus this length of the triangle. So basically what's happening here is we have this triangle. I know this is 3 and this is 9. But obviously water is, the volume is decreasing. So we're going to find the volume at some other height. So right here, this R and this H are proportionate to 3/9. So what I am going to write is I'm going to write a ratio here. R over H is 3/9. Yeah, hold on. And then now I could simplify that. Let's simplify that on the right. R over H is just 1/3. And now what I can do here is, since I'm trying to find dH dt and there's no information about dr dt, I'm going to solve this for R. So if I multiply both sides by H, I get R is equal to 1/3 H. So here, what I did was I multiplied both sides by H, and I get R is equal to 1/3 H. Now I can plug this into the R, and now I have an equation only in H, because the information in the question only tells me things about the height changing. It doesn't give me enough information about the radius change. So what I'm going to do is I'm going to change this equation to V equals 1/3 pi 1/3 H squared times H. So what I did was I took this and I plugged it into the R. Now I'm going to clean this up a bit. 1/3 squared is 1/9. So let's just, so this is, I'm going to just combine 1/3 times pi as pi over 3. And this is going to be 1/9 H squared times H. And so after I multiply it again, this is really just pi over 27 H to the third. And now I have a nice little equation here that I can differentiate. I don't need any product rule. I could just go ahead and differentiate this now. It actually makes the question easier. Yeah, Abraham, did you have a question? No. Oh, okay. There's a lot of questions. It's many questions. So we are going to differentiate dV dt. Okay, now we're going to do our power rule. What's 3 times pi over 27? Which reduces to what? Pi over 9, right? And then this becomes H squared dH dt. And then now we can just go ahead and plug in our numbers here that I know. Our dV dt is -1. This is pi over 9. Our H is 3. And this is dH dt. Oh, this is actually easy because what's 3 squared? And so the 9 on top, 9 on the bottom cancel, right? Okay. So it's -1 is equal to pi times dH dt. And then I could just divide both sides by pi. And so dH dt is equal to -1 over pi, what is this, centimeters per minute. And let's say you had to put it in a calculator, you could do that. And this is, I'll just give you the number. It's -0.318 centimeters per minute. Okay. So why don't you go ahead, try example 2 on your own. It's the same exact problem. The numbers are just different. Okay. It's another cone. A water tank has the shape of an inverted circular cone. Right? A cylinder. Yeah, I know. I don't know who would make a tank in the shape of. No, because if you want to like take stuff out, it usually drains from the bottom, and you wouldn't want to just like spilling like that, right? Okay. So you want that little like tip on the bottom for it to. Okay. I'll be right there, Chris. Yeah, so everyone try number 2. It's the same exact problem, just different numbers. So here's the solution. Let me show you the steps as we go along. So I have the volume. Daniel, copy this. The volume, this is our volume equation. Remember, you need to replace R with something because there's no information about the radius changing. So I'm going to go ahead and do this on the side where my cone, right? The radius is 2 and the height is 4. So R over H is 2 over 4. And then I get that R is equal to 1/2 H. Once you get that R is equal to 1/2 H, now we could plug that in for R here. And so this is 1/3 pi. And then this is 1/2 H squared H. One-half H squared is 1/4 H squared. If I multiply all of this out, it gets pi over 12 H cubed. Now, if I differentiate both sides, I get dV dt is equal to pi over 4, because H squared dH dt. And then now I plug in 2 for dV dt. I plug in 3 for H. Question, Chris? No, right here. The water is 3 meters deep. Okay, the height of the cone is 4, but the water level is changing, right? So here, this is going to be 2 is equal to 9 pi over 4 dH dt. And then just to solve this, I multiply both sides by 4 over 9 pi. Let's multiply by the reciprocal to cancel. And so I get 8 over 9 pi meters per minute. Yeah? Second problem's not too bad. Now, let's go to the next page. Yeah, I know. That's what I was talking about earlier. And no, don't. What happened was Algebra 2, when I made their copies, I needed it to be flipped like upside down because their pages were horizontal and it's less confusing. But then once I put yours in, it followed the same setting as theirs, and yours went upside down too. Sorry. Okay, now let's go to example 3. So everyone look at this one. This is a different type of problem. They sometimes like to ask, a person who is 6 feet tall is walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate that the person's shadow is lengthening? Okay. So here's the situation. We have a street light. I don't know, whatever you want to put here. Whatever, I don't know what that is. Okay. And there's your street light. Okay. Now, someone is walking away from the base of the street light, so someone's right here. Now, what's happening is the light is shining, but the way the shadow forms is the shadow forms behind the person, right? And so what happens is there's a triangle forming here. Okay? Where this is the shadow. And so we want to know how fast the shadow is changing. So I know that this is 6 and I know that this is 15. Good. Now, so one thing that we are now, if I turn this into a geometry problem, this looks like a triangle you probably seen in geometry where there's like this thing in the middle. And now this is 6 and I know this is 15. And let's just call these different letters. I'm going to call the distance how far the man is from the light pole as x. Okay. So this x is the distance. I'm just going to label it for one problem so you know what's happening here. This is the distance from the street light, from the light to the person. And then now we're going to call this, I'll call this a different variable. I'll call it z. I'm not going to call it y because y is usually a vertical thing. So z is the length of the shadow. Now, what we're going to do is we could write a proportion here. So once again, this is another geometry fact that if you have this line in the middle, this small triangle here is proportional to the big triangle. I don't know if you remember that from geometry, right? This small triangle is proportional to this large triangle that's here. So what I'm going to do is I'm going to set up a proportion. Now I'm going to set up the big triangle to the little triangle. Now, the height of the big triangle is 15. And the length of the big triangle is what? So this is the big triangle. What's the length? What's the base of the big triangle? Huh? Not x times z, x plus z. So this is the height, this is the base. Now for the small triangle, the height is 6, but what's the base? Not z minus x, it's just z, right? Z. Now, first, before we start solving this equation, what are we looking for here? Let's go back to the question. The rate that the person's shadow is changing. What variable did we call the shadow? Z. So now what we're looking for in this problem is dz dt, right? That's our question mark. Because, oh, I didn't do it. It's okay. Yeah. Don't even know where I put it. Oh, I think it's up there. Okay. Oh, it's right there. So now what am I going to do is what I normally do when I get a proportion. What am I going to do? No, we're just going to cross multiply. Like going back to geometry, we're just going to cross multiply. And I get 15z is equal to 6 times x plus z. Was that a groan, Daniel? No, this one. And then now we just distribute. 15z is equal to 6x plus 6z. You don't have to call it z. You can call it whatever letter you want, by the way. The letters are arbitrary, the x and the z. Now, of course, I'm going to combine my z's. So this, I'm going to subtract 6z from both sides, and I get 9z is equal to 6x. And then now we have an equation that we could differentiate. I have z, I have x. So this just becomes 9 dz dt is equal to 6 dx dt. And then I'm just going to solve for dz dt. I'm going to divide both sides by 9. And I'm going to plug in what dx dt. So dx dt, it says a person is walking at a rate of 4 feet per second. Now, is the person walking away from the light or towards the light? Away. So if they're walking away from the lamp, is x getting bigger or smaller? Bigger. So dx dt is going to be positive, right? And so the 4 feet per second is our dx dt. So our dz dt is 6 times 4 over 9. And I get 24 over 9, which can reduce to 8 over 3 feet per second. 4 is in the problem right here. So in the problem, our dx dt is 4. It's a given in the problem. It says that the person is walking away from the base of the street light at a rate of 4 feet per second. So that's our dx dt. Now, go ahead and try example 4, letter A, which is the same as example 3. And we'll actually do the FRQ on the back tomorrow. So don't worry. So everyone try example 4, letter A, please. Example 4, letter A. It's exactly like the problem up above, except the lamppost is a different height. The lamppost is a different height, but I think the person's the same height. Oh, I forgot to mention, the man is 6 feet tall. Let's just use the same one as before. There wasn't enough information here. So no, I'm gonna give you the information you need. A man is 6 feet tall. For example 4. Okay, so let's work on the problem, Abraham. Oh. Okay. 4A. Everyone work on 4A. And then I'll show you how to do 4B. So I have 26 over x plus z is equal to 6 over z. Now, so once you cross multiply and get it, you should get 20z is equal to 6x, which is 20 dz dt is equal to 6 dx dt. I just divide both sides by 20, and I plug in 4 for dx dt. So I have 6 times 4 over 20, which is really 24 over 20. And 24 over 20 reduces to 6 over 5. Question? Okay, I'm gonna. Abraham, you have a question, Abraham? Okay, now. So letter B, at what rate is the tip of the shadow moving? Now, this is a weird question. They're basically asking, so Chris, pay attention. So letter B, Daniel, pay attention, otherwise you don't know what's happening. So letter B, at what rate is the tip of the shadow moving? So the first question is how the length of the shadow. But second question is this specific point. What is the rate that this specific point is moving? Now, the way we're gonna find this tip is the tip is being affected by two different rates. How fast the man's walking, because if the man keeps walking, this tip is moving. And then also the length of the shadow, if it's increasing or decreasing, is also moving the tip, right? So this one's actually really simple. All you have to do here is just add the two derivatives, dx dt plus dz dt, because it's being affected by two different rates. So that tip, we are just going to add 4, which is our dx dt, and our 6/5, which is our dz dt. And then obviously, if I'm going to make it into like fractions, which 4 is really 20/5. I get 20/5 plus 6/5 is, and the final answer is 26. I know I was doing this really fast during our meeting this morning. It's 26/5 feet per second. Well, 4 with a denominator of 5. Oh. Yeah. Yeah. And then now you, right, because it's an area of a circle. So the formula you're using is A equals pi r squared.